grapefruit moon, one star shining, shining down on me.
Welcome to our 22nd lecture here in Chemistry 51C at UC Irvine. We just finished an extended weekend holiday due to the Thanksgiving break. It just seems a little bit difficult to get back into the swing of things, so I really appreciate the fact that you're coming here to my lecture live, or if you watch it on YouTube or a recorded version of it, that's great too. Just as much exposure as you can get to the material is awesome. I was making some grapefruit this weekend, supreme style, cutting out the segments and then squeezing the juice on top. And it reminded me of the fact that some people have to be very cautious about consuming grapefruit if they're on very particular drugs. And so I wanted to talk about this issue for people who are taking certain drugs, why they shouldn't be taking grapefruit. And this is a pretty well-known phenomenon, I think. I tried to trace back the origin of how this was discovered. Who was the first to discover that you shouldn't be eating grapefruit if you're taking certain drugs? And I traced it back to some study. I don't know exactly who the main authors here. I think maybe David Bailey is one of them. And they were doing a study of these calcium channel blockers like phenolidipine. Amlodipine is a newer one that you take if you have high blood pressure. Of course, calcium controls the contraction of muscle cells, including smooth muscle cells that line your blood vessels. And so if you want to stop your blood vessels from contracting so much and giving you high blood pressure, you need to take a calcium channel blocker that's selective for those smooth muscle cells. Phenolidipine is one of those. And they were conducting a study to see, to test the effects of phenolidipine, as I understand it. And that's how they discovered this effect of grapefruit juice. I'll read a little line from one of Bailey's later papers where he says, the novel finding that grapefruit juice can markedly increase oral drug bioavailability was based on an unexpected observation from an interaction study between the dihydropyridine calcium channel antagonist phenolidipine, that's this thing here, and ethanol, in which grapefruit juice was used to mask the taste of the ethanol. So they were trying to do some sort of a trial on humans, and some people were getting phenolidipine in ethanol, and they were trying to hide the taste of the ethanol by using grapefruit juice. And they discovered some other effect of the grapefruit juice. And let's go and talk about this, because what they're saying is that grapefruit juice makes the phenolidipine hang around in your body longer than you want. And if you're a pharmaceutical chemist who's interested in pharmacokinetics, which you should be, then you have to worry about that. I got this great diagram here from a later paper by Bailey, where he has a really good description here. I'm going to draw two of the key organs. When you ingest drugs orally, take some sort of a pill, that's more usual. It'd be very unusual to take maybe a liquid form unless you're in the hospital. Here's a picture of the liver, and let me see if I can draw a picture of the stomach. I don't have pink, but I'll use, that's a nice pink. This will be the picture of the stomach. And so when you ingest drugs and they go into your stomach, your body has to process all foreign molecules in some way. And so one mechanism is to transport some of the things that get absorbed into the liver through the portal vein. And there they get metabolized. And so here's a picture of a liver cell right here. And you can watch what's happening. What it's telling you is that as the drug enters the liver cells have enzymes in them that try to degrade foreign-looking molecules. The liver cells are saying, this doesn't belong in the human body. Let's try to oxidize it or cleave it or react it in some way. So that's what liver cells are doing. And there's another location where you see metabolism occurring, and that's once these compounds enter the gastrointestinal tract down to the small bowel here, they're also getting absorbed into potentially into the bloodstream. And there are cells here in the small intestine that also contain that same enzyme, CYP3A4, cytochrome P450 3A4. CYP enzymes are enzymes that try to oxidize the heck out of formylapine molecules. And let's take a look at what these CYP enzymes do to phenolapine, and why it matters whether you're drinking grapefruit juice while you're taking phenolapine pills once a day to control your high blood pressure. So the CYP enzyme is critical for degrading this calcium channel blocker, phenolapine. It just happens to be there's many CYP enzymes in your liver and throughout your body that degrade drugs. This particular one, it turns out, oxidizes this it pulls off a hydride group from that dihydropyridine ring and turns this pyridine into a fully aromatic pyridine ring. And you need it to do that, because once the CYP enzyme oxidizes this, this is no longer active, and then it gets cleared from the body. And you need it to be cleared from the body, because the next day you're going to take another pill. And the day after that, you're going to take another pill of phenolapine. And the day after that, you're going to take another pill of phenolapine. It is essential. And the drug has been tested assuming this, that the phenolapine will be metabolized and then passed out of the body. The problem is that grapefruits contain a class of compounds called furanocoumarins, such as bergamotin. That's one of the molecules that you find inside of grapefruit juice. And this bergamotin molecule also gets oxidized by CYP3A4, this enzyme. But the pernicious effect here is that CYP3A4 has this thiol group in there, I'll draw it as a thiolate anion, that then reacts chemically with this epoxide that's formed. And so bergamotin ends up covalently attached to the CYP enzyme and ruins the enzyme. And so now, because the enzyme doesn't function anymore, because the bergamotin ends up covalently attached to the CYP enzyme and inhibits it permanently, forever, now your body can no longer degrade phenolapine, and the phenolapine builds up. You take another pill the next day, you're just adding more and more and more phenolapine to your body, and that's not good. So most drugs, pharmaceutical chemists are planning for the fact that they are going to get degraded. That is good for any drug that you're going to take a pill a day or more frequently, but you want the drug to be metabolized properly and to get out of the human body. So if you go to a medical school or pharmacy school or one of these other schools, you'll end up taking a pharmacology class, and you'll talk about metabolism. Maybe this is a pretty classical example of that. Okay, let's return to our lecture material. We've been working on chapter 25. And this is where we left off. Now, I want to encourage you in this class to take advantage of our office hours, to take advantage of our discussion sections. We've noticed a decrease in engagement in our class over the quarter, and I know it's hard to stay engaged, but you can't wait until right before our last exam and say, hey, Professor Van Vranken, or to the TAs, I need help because I'm afraid of not passing the class. We're there during our discussion sections. We want you to just come and sit and work problems. And whenever you can think of a question, ask us a question. And if not, just sit there and continue to study or something. Take advantage of that. Take advantage of our discussion sections. We're working through problems to help you build the skills you need in order to do well on the exams. You shouldn't be thinking, well, I'm too embarrassed to go to discussion section because I don't know all the answers. Well, that's exactly what discussion section is for. We don't want you to come there if you know all the answers. Well, actually, we still would want you to come because it's still good practice. Nobody knows all the answers, even me. Okay, so please take advantage of those. We provide those opportunities for you, for our department peer tutors, our TAs, myself, for you to take advantage of those. And so we expect you to attend discussion section and office hours, and to take advantage of those, to keep talking about organic chemistry and getting help with sapling, with just problems you're working in the textbook. And your real goal in this class is to work as many problems as you can, because I'm going to give you problems you've never seen on our exams. And so you have to work as many problems as you can to build your tools. Now, we're in chapter 25 in the Gorzynski-Smith textbook, in the fifth edition of Gorzynski-Smith, and we've been talking about amines. And we left off talking about amines as acids and bases. We talked about amines as nucleophiles. They're not very useful for just simple SN2 reactions, because you often get over-alkylation of the amine. But now we're talking about attacking protons, where amines act as acids and bases. And I showed you this simple way to estimate at equilibrium what are the ratios of the amine and the ammonium ion when you combine it with any acid in a synthetic organic chemistry flask. And I told you, when you're in a laboratory and you just dump stuff into a flask, it's usually not buffered conditions. If you have a buffered condition, like a cell or the human bloodstream, the plasma or serum inside the human body, or if you're working in a biochemistry lab making buffered solutions, then you use the Henderson-Hasselbalch equation. But that's not really the way we're doing things in an organic chemistry class or an organic lab. We're not really talking about buffered solutions typically. We're just dumping things together and letting them see which one ends up with the proton. And there, as long as you know the pKa's of the two acids on each side of an equilibrium, so here's an acid-base reaction, and here we're trying to ask, is it plausible for hydroxide to pull a proton off of an amine? Or is it the other way around, that the resulting amide anion would pull the proton off of water to give you back the hydroxide? And I showed you a simple equation. You just take the difference between the pKa's, and that will tell you the ratios of the two species. It tells you that the ammonium ion, the amine versus the amide anion, there's going to be way more amine present. And you could figure that out just by saying KEQ equals 10 to the power of product pKa minus reactant pKa. You have to look at the acid on each side. And even I can subtract two numbers. The challenge is to memorize the common pKa's of amines and water and the common functional groups in organic chemistry. Okay, pKa matters a great deal if you're headed off to be a dentist or a pharmacist or an MD of some kind, because whether molecules are charged or neutral controls whether they can pass through biological membranes and really enter the human body. And that's what you want to know. Let's go ahead and think about that a little bit. What is the how to think about that? I want to take an example of an amine, and I'm giving you two different situations where I've got an organic solvent and an aqueous solvent, and they've been mixed together and then allowed to form two layers. And if I put an amine in this first beaker that has two layers, it's going to partition between these two layers. Where would the amine end up? Well, if you have hydrochloric acid in the aqueous layer, that amine is going to end up protonated. So I'll take an example of a cyclic amine called piperidine. It doesn't matter whether it's cyclic. And because there's HCl there, you expect that to be almost all protonated. This is not a buffered reaction. You'd have very little of the unprotonated piperidine. You could use that equation on the previous slide and just estimate, what's the relative pKa of HCl versus an ammonium ion. It's a huge difference. It's like 17 orders of magnitude difference. Now, and so if you had HCl in the aqueous layer, then really you'd end up with this pyridinium chloride in the aqueous layer. But if instead I treated that with sodium hydroxide, if the aqueous layer had sodium hydroxide, there's not going to be piperidinium ion in there. It's going to be the neutral amine. And I just showed you on the last slide that the sodium hydroxide is not strong enough of a base to make the amide anion. There's not going to be N- in there, but it will be neutral. And what that means is that I hope you didn't draw that because I'm about to erase it again, is that the amine is going to be neutral. It's not going to be soluble in water. It's going to go into the organic layer because it's neutral, not in the aqueous layer. So that's where when you're extracting, when you're mixing it with aqueous base, the amine goes into the organic layer. And usually as a synthetic organic chemist, I want to isolate products of reactions. That's where I want my amine, because then I'll just pour off the ether and evaporate the solvent and have nothing but pure piperidine in there. Because I always tell you that organic chemists like to isolate neutral compounds. There's no simple way to evaporate the water. It's hard to evaporate water. Ether almost boils at room temperature. That's easy to evaporate. And I won't have any annoying salts left over. Why is this important? So it's important because ether is kind of like a biological membrane. And let me just make that comment here that ether is like a biological membrane for the when you look at most drugs that are prescribed as pills, most drugs that are prescribed as pills are amines because they spend some time protonated, and when you're closer to pH 7 or slightly above, and they spend some time deprotonated and neutral so they can fly through membranes, and this gives them the ability to be soluble in water, in cytoplasm, in human serum, human blood plasma, and also spend some time, every in the neutral form so they can cross biological membranes and make it from your stomach into your bloodstream through the blood-brain barrier or places like that. So it's important. It's important for medicines and drugs to be able to cross biological membranes that are very much like organic solvents. Let's go ahead and take a look how there's a practical application of this. And so let's go ahead and take a look at a process called freebasing. So if you were doing cocaine this weekend and you bought some nice white powdery coke from your dealer, this is the general structure of the white powdery cocaine that's fluffy and just looks pure as snow. It's the hydrochloride salt. That's how they sell that. But unfortunately, if you snort the hydrochloride salt, very little of it can cross through your nasal membranes and make it into your brain. And that's because it's just sitting there in your snot and it'll just kind of drip down and numb your throat maybe, but it's not going to cross, very little of that is going to cross through the barrier. What you're relying on in order to get the effects of cocaine is you're relying on the fact that there's a small equilibrium amount of that when it's in a buffered biological fluid that exists as the free amine, and that can freely pass through membranes. So I'll just write here that passes through membranes, like the nasal epithelium. And then it can go right to your brain, straight to your brain. So if you really want the cocaine to go straight to your brain, isn't there some chemical you can mix it with and convert it all to the free basic form? Of course there is. What you do is you go to the grocery store and you buy some Arm & Hammer baking soda, that's sodium bicarbonate, and then you heat the heck out of this. And the bicarbonate, it serves as a base that generates carbon dioxide and H2O and sodium chloride. And so if you heat this with sodium bicarb, you can even heat it up enough to where some of this vaporizes and goes straight into your nasal passages, right through to your brain, gives you an immense high. And they sell the free-based form as it's this waxy solid called crack cocaine. Very easy to pass through membranes. It just doesn't look nice and white and fluffy. So that's called freebasing. And the concept of freebasing is not just cocaine. In the laboratory, anytime we take an amine that's a hydrochloride salt, hydrobromide salt, sulfuric acid salt, anytime we strip off the acid and just reveal the free base, we call that freebasing. But now it has this drug use connotation to it. When you get to, we need to talk about more about the ease of protonating amines. And I want to distinguish amines from a functional group that we would refer to as amides. So let me go ahead and draw out an amide functional group. Here's an amide. And if I wanted to think about where I would protonate an amide, like if I treated an amide with some sort of an acid, it doesn't matter whether it's hydrochloric acid, sulfuric acid, hydrobromic acid, toluene sulfonic acid, where is it going to protonate? The answer is that it's going to protonate on oxygen, not on nitrogen. Not ever on nitrogen. Never, ever, ever, ever on nitrogen. Not ever. Let's go ahead and understand why you would never protonate on nitrogen, because if generally amine lone pairs are more basic than oxygen lone pairs. So what's up with that? Well, the amine lone pair is basic and it is a strong donor group. And the problem is that long before this collides with an HA molecule, those lone pairs are donating into the carbonyl. And so, right, let me go ahead and draw the most important resonance structure for an amide. In fact, Linus Pauling was the one who pointed out, Linus Pauling said, when I look at an amide, that's the basic functional group in proteins, it looks to me like it's about 60% CO double bond and about 40% CN double bond. And there's not one resonance structure that's perfect for describing an amide. You have to envision both resonance structures at the same time. And so when you look at this bottom resonance structure, why would you ever want to protonate that bottom nitrogen? You never would. There's no reason. If I showed you this bottom resonance structure, I think it's a lot easier for you to guess where it's going to protonate. Of course, it's going to protonate on the oxygen. I think you can see that if you start with the bottom resonance structure, it's more obvious that you're going to protonate on the oxygen and that you would never protonate the nitrogen, right? And this is just giving you a resonance structure of the final product. So never ever protonate the nitrogen of an amide. The carbonyl group that is attached to the amine in an amide completely changes the character of that functional group. Okay, let's go ahead and think about what happens if you attach a phenyl group to an amino group. That's called aniline. So aniline lone pairs are way less basic. They're 5 orders of magnitude less basic than regular amines. And so how can we think about the fact that aniline lone pairs are less basic than regular amines? I'm going to draw an amino group that's attached to a benzene ring. And I'll go ahead and draw all the bonds here. And I want to think about how that benzene ring affects, why is it that this lone pair on an amino group is 100,000 times less basic when I attach it to a benzene ring. It's related to resonance. Just like this amide up above, I'm going to be able to draw resonance structures in which I donate that lone pair. So let's go ahead and take a look at that resonance donation for the amide. The resonance donation for the amide looks like this, right? That lone pair is donating into that carbonyl group, which is a great acceptor. We can do something similar here with the aniline and talk about why those lone pairs are not so available. That's because they're donating into the arine ring. There's lots of resonance structures I can draw here. Let me start off with this one. So here's the first resonance structure. I'm going to draw lots of them. So here's the first resonance structure I can draw. And it's not great. It's okay, but it's not great. But as soon as you see that N+, now you can kind of see why it's hard to protonate that nitrogen. But the problem with this resonance structure is not as good as that amide resonance structure, because this is not an aromatic ring anymore. So this resonance structure, and plus I'm putting the negative charge on carbon, which is not as good as putting it on, carbon's not as electronegative as nitrogen. So there's 2 reasons why this resonance structure is not as good as the one above. Let me go ahead and draw another resonance structure. I'll use more arrow pushing here to help keep me pushing this negative charge and show that it gets delocalized all over that benzene ring. There we go. That's another resonance structure. And right, I can keep pushing that negative charge on the benzene ring. There we go. I'll push it here, and then I'll give the electrons to there. Now, none of these 3 resonance structures are as good as this resonance structure up above, because this resonance structure above doesn't lose aromaticity. It's not like it started with aromaticity and lost it. And also, we're putting the negative charge on oxygen, and that's more electronegative than nitrogen. So The only bad thing slightly about this resonance structure for an amide is that I've separated charges. And you guys learned about Coulomb's law if you took a physics class. It takes energy to separate charges apart. And you could calculate how much energy that costs. But even though you had to separate charges, it's still 40% of the picture of an amide. But down here with the aniline, I've got lots of resonance structures. None of them are great. And so that's why you get an effect. The benzene ring decreases the basicity of that lone pair. So this lone pair here is not, this lone pair is not so basic because it's donating into the benzene ring, but that donation is not as dramatic as when you're donating into a carbon. But again, aniline lone pairs are not very basic. It's not as easy to acylate an anamine, get an aniline lone pair to attack a carbonyl group as it is a regular amine. Usually the reactivity is so high, of most carbonyl groups is so high, it doesn't make a difference. But there are some cases where it can be frustrating to try to do chemistry on aniline nitrogens, and you get surprised by the fact that they don't react as fast as regular amines. Okay, these kinds of resonance questions, that may seem like a lot of work to draw up those resonance structures, but the fact is when you get to questions like on the MCAT and the DAT and places like that, they love to ask you questions about stuff like aniline resonance or phenolate anion resonance. Here's an example where we expect you to have some appreciation by drawing out lots of resonance structures for the relative effects of groups that are ortho and para. So we're really talking here about, let me go ahead and use a highlighter pen here for about groups that are ortho and para to the aniline amino group. When you have groups that are ortho and para, they're at just the right position to affect those resonance structures we drew on the previous page. Let me flip back very briefly to the slide on the previous page. If we look at the positions where the lone pairs end up, they end up at this ortho position relative to the amino group, this para position, and then at this amino position. So if I have substituents at either the ortho or the para position, if those substituents can stabilize that carbanion resonance form, then they're going to have a dramatic effect on how on the basicity of that lone pair. And so let's go ahead and take a look on the next slide at how that comes into play. So if I look at the relative basicities of these lone pairs here, let me draw them. There's a lone pair. There's a lone pair. There's a lone pair. They're not equally basic. Let me go ahead and compare them to each other. I'll tell you the relative basicity. And we'll compare everything to aniline. I'll give that a relative basicity of 1. When you put a methoxy group there, it's got about the same basicity. It's a little bit higher, and you might say, wow, 5 times higher. 5 is nothing. 10 to the 5 is something to think about. 100,000 is something to think about, but a factor of 5 is not really that dramatic. The effects really get big when we put electron withdrawing groups at the ortho or the para positions, because now the relative basicity of that lone pair is 0. And I hope I get my zeros right, 0.25. I mean, that's an effect that you want to think about. So what is this effect here when you put a nitro group at the para position? I'm going to go ahead and draw some resonance structures for these. And I'm going to start off by drawing the lone pair here over here on this nitrogen. And we'll think about, why is it that that lone pair is not available to add to an acid, to a proton? Well, that's because it's already donating. Let's take a look at that donation. Right? It's already donating before you mix this compound with an acid. It's already donating. So let's start off by drawing out this first resonance structure here. It's already donating. That wasn't a very good second double bond. There we go. I don't want to forget to put a positive charge. If I have 4 bonds to nitrogen, it better be a positive charge. So here's one resonance structure. And now let me draw out the nitro group so I can see that when I have this carbanion resonance structure, I can keep pushing arrows. I'm going to keep, there's more resonance structures I can draw where that nitro group is really going to stabilize that carbanion. So let me draw another resonance structure, and we'll just keep, there's so many resonance structures we can draw here. So let me draw another resonance structure where I'll take this lone pair and I'll keep pushing it over here to the nitrogen, and then I'll push the electrons up to that double bond O, and that's great because it leaves the negative charge on oxygen, and oxygen loves negative charge. Oxygen's electronegative, more electronegative than nitrogen, that's for sure. And so I end up with this resonance structure that looks quite good. Putting negative charge on oxygen is quite good. Negative charge on carbon is not quite good. So I end up with this. This is the most important resonance structure because it puts negative charge on electronegative atoms. I'll just write this is the most important resonance. There's other resonance structures, but this one is the most important one. That's the most important resonance structure. Why? Because negative charge is on electronegative atoms, being oxygen. I mean, the only more electronegative atom would be fluorine. There's no fluorine on here. Okay, so that nitro group really stabilizes this resonance structure, and right when you look at that N plus is not going to add to any acid proton. You can't protonate the nitrogen when there's no lone pairs on it. So it's like the lone pairs are kind of gone. They're donating into the aromatic ring and ultimately into the nitro group. Let's take a look at the situation when there's a methoxy group at the para position. You might think, well, wait a second, isn't oxygen electronegative? But if we try to push those arrows in the same way, right, let me go ahead and draw the resonance structure when I've got a para-methoxy group. Let me go ahead and start here, and we'll push the arrows first. And I'll leave the electrons there so we can just stare at those for a second. We can ask, isn't this a good resonance structure? Well, it's as good as you would see for aniline, but now we're stuck. There's no additional resonance structure that we can draw for this para-methoxy aniline. It's kind of stuck right there. You can't, you have to resist the temptation. Let me draw the lone pairs on the oxygen. You have to resist the temptation to try to do this. You can't push this there's nothing. Let me make that more dashed. I want to make it absolutely clear you can't really do this. And I'll put some exclamation points here. It's like, what? I can't, you're stuck there. That nitro group, you had that beautiful resonance accepting ability of the nitro group. A methoxy group can't accept any electron density from next door. You can't deprotonate next to oxygen atoms of ethers. You can't stabilize carbanions if you put them next to an oxygen. So really, the worst thing is that the same time the carbanions trying to donate into the oxygen and can't do it, the methoxy group has lone pairs that are trying to donate into its neighbor and can't do it. You're also kind of making it a little harder for this oxygen to donate into the aromatic ring. So very frustrating. And so it's a little bit harder to protonate a methoxy aniline than a regular aniline. Okay, so I expect you to, and everybody who administers these standardized exams, they expect you to be able to think. They expect you to have had practice drawing resonance structures with electron acceptors at ortho, para, and even meta positions to understand why meta doesn't have the same effect. And if you've never drawn a resonance structure, if you think you're too busy to draw those resonance structures, then you're not going to get the practice you need to prepare for my exams or these other types of standardized exams that they use to test whether you've absorbed the material. Okay, so, and this is very similar to chapter 19 where we had phenolate anions, and we talked about how groups at ortho and para positions could stabilize the deprotonated form of phenols. Okay, so we've just looked at resonance and its effect on the basicity of nitrogen lone pairs, and now I want to switch gears a little bit to think about how does hybridization affect the reactivity of nitrogen lone pairs. And specifically, we'll look at basicity, but it usually correlates with nucleophilicity. So I've got 3 nitrogen compounds here, an amine, an imine, and a nitrile. And they have different hybridization. And the imine here, you're not going to see, I guess you would call that a shift base, or you might see an imine like that in some functional groups. But the most common type of sp2 hybridized nitrogen compound that looks like an imine is pyridine. And that's, the lone pairs on pyridine are very similar to the lone pairs on an imine. Let's go ahead and draw out just in this little table here, the hybridization. The hybridization of the nitrogen in an amine is sp3 hybridized. There's 3 bonds to nitrogen and 1 lone pair. Now, when the nitrogen is part of a double bond, now it's sp2 hybridized. The angles are trigonal, and that's between lone pairs and protons or double bonds. And then finally, when we have a linear arrangement like this nitrile, that's sp hybridized. And what's changing here that you need to focus on is the p character. How much p character is there in that lone pair, in the hybridization of that lone pair? Because p character corresponds to basicity and nucleophilicity. More p character means more basic. More p character means more nucleophilic. And the differences are not small, they're massive. Let's take a look at how a little bit of extra p character translates into ability to attack protons, that is basicity. So I'm going to compare everything to the sp2 case. We're just going to talk about relative basicity. So I'm going to assign imine with a relative basicity of 1. That's because we don't have a common scale or a set of units that you would memorize. And relative to that, if I compare pyridine, for example, to piperidine, if I compare an sp2 hybridized lone pair versus an sp3 lone pair, the sp3 lone pair is 100,000 times, let me make these 1 digits places line up here, is 100,000 times more basic than an sp2 lone pair. If you had to go get a job somewhere and one person offered you a salary of $1,000 and another person offered you a salary of $100,000, which job would you take? A factor of 100,000 is a huge difference. That's where we start to pay attention. And the situation is reversed when you have very little p character, as in this HCN molecule. When you're an sp hybridized, and you may think, well, if you look at the percent p character, it's like 75% p character, 66% p character here, and then 50% p character here. It seems like such a small difference, but look at the difference it makes. When I go down to the sp hybridized, it's going to be 0. Whoops, let me draw with my red pen here. It's going to be 0. Boy, I hope I can get this right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think it's about 10 to the minus 15. Man, right? You'd think that all nitrogen lone pairs are the same, but they're not. If from day 1 in this class, if you haven't been paying attention to hybridization, I have no idea how you've made sense of anything that we've been talking about, because it's more important to know the hybridization than to know whether that's a nitrogen or oxygen. So more p character means more nucleophilic and more basic. I hope you've been paying attention to p character, because without understanding this simple fact, more p character means more nucleophilic and more basic. There's no way to make sense of organic molecule reactivity. Okay, so this kind of is related. How would you know whether something's sp2 or sp or sp3? You really have to take a look at resonance before you draw those conclusions. Let's go ahead and take a look at some nitrogen heterocycles. And I can't remember. I think we talked about this in an earlier chapter in the quarter before this, Chemistry 51B. There was a chapter on heterocycles, I think, or on aromatic heterocycles. Let me go ahead and draw out some aromatic heterocycles, because I want us to be able to draw conclusions about which of these nitrogen lone pairs are basic and which are not very basic. So this is called pyrrole. The first molecule is pyrrole, the second molecule is called piperidine. And then this third molecule, which is a 5-membered heterocycle, is called imidazole. This is the side chain of the amino acid histidine. And there's a simple rule that we have, and that is that if you're in an aromatic ring that contains nitrogen, we refer to these as nitrogen heterocycles. And this could be a DNA base like adenine. It's the same idea. The idea is that lone pairs on nitrogen that are attached to double bonds, the first rule we're going to have, attached to double bonds, that lone pairs on nitrogen that are attached to double bonds, not part of the double bond, are not basic, and especially when they're part of an aromatic ring system like these. So here's a nitrogen atom in pyrrole that's attached to 2 double bonds, but the nitrogen itself is not part of a double bond. And so the conclusion is that these lone pairs on this particular nitrogen versus this, or these 2 lone pairs over here, these lone pairs right here are not basic because they are attached to double bonds. The lone pairs are donating into the double bonds by resonance. But when we come over here and we look at lone pairs that are part of a double bond, like this one right here, well, that's very similar to these over here. They're a little bit basic. So I'll just go ahead and write a little bit basic. As opposed to not basic at all, right? Sometimes we use pyridine just to soak up hydrochloric acid, right? It can pick up a proton from hydrochloric acid. Then finally, this proton over here is also sp2 hybridized. It's part of a double bond, right? It's part of a double bond. That you can see an NC double bond there, so it's a little bit basic. And then finally, we come over and we look at this one. And which category is that in? Well, the nitrogen is not double bonded to anything. It's not part of a double bond, but it's attached to 2 double bonds. And so, like we just said, according to this rule over here, right, that's not basic at all. It's not part of a double bond, but it's attached to 2 double bonds. So it's not basic at all. So when you look at the side chain of the amino acid histidine, it may look like both those nitrogen lone pairs are the same, but the enzymes that use histidine for catalysis are only using the lone pair. They only use the lone pair over here for catalysis. They don't use that other lone pair to pick up protons. All right, now there's 2 extra sections in the book. One is amines as nucleophiles, and it's a review. You can use amines. If you're smart, you'll use amines to attack carbonyl groups, acid chlorides to make amides, carbonyl groups to make imines, like if you add aldehydes and ketones. Amines, as for doing SN2 reactions, are kind of hard to control. You get overalkylation, and that's why you use other types of nitrogen derivatives as nucleophiles, like phthalimide anion, as an example. There's a section of the book called Hoffman elimination, and this was really all the rage back in 1851. Everybody was talking about the Hoffman elimination when it was discovered and how great. You know what? It's not 1851. That's like, there's no reason for you to be learning that. I'm not going to ask you any questions about that. If you want to read it and see some cool historical information, cool, but I don't understand why the book puts that in there. Doesn't seem like it's relevant enough for me to test you on that. I'm not going to test you on that. But I hate to say don't read stuff because it's always cool, but I'm not going to ask you about that. All right. The last part of this chapter has to do with an area of chemistry related to something called nitrous acid, and this is the main last section of chapter 25. So I'm going to go ahead and stop right there. Because this all fits within a section of the chapter that I can't finish covering today. So what did we talk about today? We talked a lot about the reactivity of nitrogen lone pairs and how resonance can dramatically affect the basicity and nucleophilicity of nitrogen lone pairs, how hybridization has a huge impact on the reactivity of nitrogen lone pairs, and about how whether a nitrogen lone pair is protonated or not determines whether it's going to be soluble in organic solvents or not, or able to cross through biological membranes. which is important. Even if you don't become an MD, if you're just a regular organic chemist like me, that's a consumer of pharmaceutical, that's an important idea. Okay, please go to discussion sections and please go to office hours. That is just super important for you to get contact, be willing, you don't have to go to office hours and ask questions. You can just sit there and say, I'm just going to work on sapling problems in my online homework, or I'm going to work problems out of the book. And if you don't think of any questions, don't ask anything, but at least we're there. The worst thing is to have a question when you're not in office hours, and who do you go to for help? I hope you don't go to YouTube or Chegg or some other thing, because they're not as good as we are. I promise you, they're not going to be good as just asking us the question while we're right there in front of you. All right, you guys have a welcome back from the extended weekend, and keep working problems every chance you get.